Okay, so in the last few videos, we just introduced the derivations of the LDA and QDA. But to implement this with real data, you need to know the parameters like mu C, QC, right? Mu C, mu D, and sigma C, sigma D. Or in the linear discriminant analysis, we need a sigma and mu C, mu D. So in other words, in QDA, we need mu C, sigma C, okay, mu D, sigma D for each class, sorry. In linear discriminant analysis, we need to know the number mu C, mu D, and we assume they have the same common variance. So same common standard deviation, sigma. Okay, but now the question is, how do we get these numbers from the data? How can we get parameter estimates from data? Okay, so that's another technique we need here. I'm gonna introduce in this short video. It's a technique, very popular technique. It's famous in the statistics. It's called maximum likelihood estimation. Maximum likelihood estimation. Okay, this is derived by the famous statistician called Fisher. In 1912. So, so let's give some motivation example. So we flip a coin. Let's say 20 times. Okay, and we observe, let's say 10 times. 10 times. And we observe it has 2 tails. So now the question is, based on this observation, what is most likely value of P? So what's this P? P is here is you toss a coin, what's the probability you get head? Probability getting a head. Okay, so how do we answer this question? So we need to assume some distributions first. So we assume we have some data. We have x1, x10. So this is the result of flips. We follows the IID distribution with the binomial distribution. Binomial distribution has 2 parameters, n is how many times we flip the coin, and the p is the success rate. So, and the p is the parameter we want to estimate. Need to be estimate. Okay. Actually, assume this is our model. Then the probability this x1 plus x10 equals to 8. So which xi equals to 1 or 0, right? Means if you observe a head, you get 1. You observe tail, you get 0. So we observed 8 of the heads, means x1 plus x8 equals to 10 equals to 8. And by the binomial distribution formula, we know this is nx, p to the power x, 1 minus p to the power n minus x. So here our x is 8, n is 10. So out of 10, so the combination of the 8 out of 10 was the probability p to the power 8, 1 minus p to the power 2. And this is a gives us formula. You can calculate this one. So this is just 10 times 9 times 3, right? And 2 times 1, actually 2 times 1 times 8 times 7 times 1. So we can simplify this a little bit. We can get 45. So 45 p to the power 8, 1 minus p to the power 2. Okay, so now this is called the likelihood function. Okay, likelihood function is a function of the parameter given the data. And MLE denotes the maximum likelihood function. Estimator. Okay, so in other words, we need to find a p such that this likelihood is maximized. So the idea is find a p that maximize LP. Okay, so this is our LP. So actually, for example, this function is proportional to p to the power 8, 1 minus p to the power 2. We can plot this function easily, right? P is p takes value from 0 to 1. Okay, so probably this function will have the shape looks like this. Okay. Actually, we can plot it exactly value. So I think that's the last plot I have here. Okay, so and from this likelihood function, we can find a point that maximizes this likelihood function. This gives us p equals to 0.8. Okay. Actually, you can derive this function how do we maximize this function? Actually, we can derive the formula analytically. So to find the maximizer, we just find the derivative with respect to p and set equal to 0, right? So this is equals to 8 times p to the power 7, 1 minus p to the power 2, plus p to the power 8, and negative 1 minus p, 2 minus p. So, and we set this equal to 0, and then we divide both sides p to the power 7, p to the power 7, we can get. So this equal to 0 is equivalent to, say, 1 minus p, 8 times 1 minus p, and we can also multiply 1 minus p, 1 minus p, both sides. So 0 divided everything is 0, right? So we can get 8 multiply 1 minus p plus p minus 2 times p equal to 0, right? And we have 8 minus 8p minus 2p equal to 0. We can get we can add 10p both sides, so we can get 10p equals to 8. So therefore we get p equals to 8 over 10. So this is the MLE, maximum likelihood estimator for the p. So therefore this is the but this is makes sense, right? Because if we toss a coin 10 times, we observe 8 heads. So the most likely value for p is 8 over 10, 0.8% chance. So that's the idea of the MLE, maximum likelihood estimator. But for Gaussian distributions, okay, we have for example, we have two classes, have x1, xn, IID from some Gaussian distribution with mu and sigma square. Okay, we can derive the likelihood function. We have two parameters, mu and sigma, right? Mu and sigma square, given the data x1, xn. This is nothing but the product of their density. Multiply fn, xn. Okay, and we take a log. So we get, usually we use a capital L to denote the likelihood function. And after taking the log, it's called log likelihood function. This is called log likelihood function. So this equals to, take the log, or you can think it's natural log f1 x1 plus natural log fn xn. Okay, so this equals to summation. So each of the term has Gaussian density. So we have the summation from 1 to n, negative 2 sigma square xi minus mu minus d natural log square root of 2 pi. So this is a constant, no parameter involved. So when we maximize this function, this term does not matter. Okay, and minus d h log sigma. So we should have parentheses here. Okay, and we want to find the maximum value for mu and sigmas, right? So we are looking for the gradient functions. Gradient functions with respect to mu, we set equal to 0. And set the gradient with respect to sigma square, we set equal to 0. So this implies, I will omit the derivation here, just tell you the formula. So the MLE for mu equals to 1 over n sigma xi. So which means MLE for the mu is just a sample mean, right? Which makes sense. Sigma square, so variance estimate is just 1 over d times n, summation I from 1 to n, xi minus mu square. So this is a MLE for the variance. And once you obtain the mu hat, you plug in here. You can calculate this one. Okay, so therefore, so now we can just apply this MLE to our Q discriminant analysis. So for QDA, okay, we estimate mu C for each class. Okay, and we also estimate the sigma C hat for each class. And for the prior probability, this sigma C, we just use the sample proportion. So the number of the data points in class C divided by the total sample size. So divided by total sample size. Okay, so for linear discriminant analysis, so we estimate sigma square equals to 1 over dn multiply by so your summation over each class, right? For I such that yi equals to c, xi minus mu c hat square. Okay, so what by the maximum likelihood estimator we can obtain all these estimates. So this is also called in statistics, this is called pooled within class variance. Okay. And for the LDA, we just compute one variance because we assume each class has same variance. And each sample point contributes contributes with respect to its own class mean. This gives very different results than if you simply use a global average. It's usually smaller than the global average, and we say within class because we use each point distanced from its own class mean. But the pooled means because we we then pull all classes together. Okay. I think that's all I want to cover today. Thank you.